Okay, we start up. Any questions before we begin? Everything is okay? Let's see if I can put out this next report exercise at the end of the week. It should be possible. From next week on, then we have to start fighting with combustion. So that's sort of the last piece in this course. Today, modifying icoFoam. So I'm going to introduce temperature into the icoFoam solver. Put in a new equation to solve. First of all, just to recap here, our equation system. When you have incompressible flow, you have the following set of equations. Continuity is just a divergence equal to 0. And you have the momentum equations, which now should read something like this. Total derivative equals, and then we will have the pressure gradient here, and we have, if you like, the gravity, and finally the viscosity. Sort of the simplest form of the Navier-Stokes. Treating viscosity as constant, density is of course constant. And then finally the energy equation, which we have sort of a neat little form, rho CV, and then we use temperature as variable. You don't need to use enthalpy. Equals, and here we will then have conduction, double derivative of the temperature, and finally the energy dissipation function. The whole idea now, when it's incompressible, is the following. The two first equation stands alone. They are not dependent on the temperature at all, especially this guy if you treat him as a constant. So you can sort of split your problem here. So you don't have to solve the temperature equation when it's incompressible. You can if you want, as we are going to do today, but they are, say, decoupled. For the energy equation, for the temperature, this one is fairly small anyway, so we do it easy. We neglect him. So our problem then, solve the flow field, velocity, pressure, and then afterwards find the temperature. So that is our topic today. Let's see if we can make this one work. I have to do it like that, I think. Like that. So, the light. So yesterday we looked at how to modify this icoFoam. So I put in a folder for you, programming icoFoam, and here now you will find here a recipe what we did yesterday. Just a cute little text file. So today we will going to continue with this one. 2312. Yeah. And what we did here, sort of creating your working area, where you can put your own, say, solvers, whatever you want, and play with them, compile them, and then you have your own version of whatever you want. the idea is you copy the original source code and change it so you don't destroy the original. That's quite essential. And then this one, very essential. You have to change this address where he should put the executable files, not in the original Foam app bin. That's the original ones. But Foam user, that's your own private area. So you have to add user into this file. The name here, you can invent whatever you want. So it doesn't have to be the same, of course, but you can create your own name for your own solver. So then what we did, we changed or added some code lines in the icoFoam.c just to print out the velocity at that location, just below the moving lid in the cavity case. And then compile and link with wmake. So that was yesterday's topic. Today we will then do it a little bit. That was too much. One back. Where are we? Here and here. We're going to create the isothermal foam. So you have everything listed here, what you have to do to make this work. So I'll go through this sort of step by step. Switch computer. Something like this. And then we should have it here somewhere. Let's see now. Here we should have it. Yeah. So this is the recipe you have been given for today's sort of setup. How to insert the temperature equation into OpenFoam. Let's see now. I am now standing in my run folder. If you go one above, you will, after you have done this at least once, you will have two more subfolders next to your run folder. One will be the application. That's where you put the source code. This one will be generated if he succeeds in compiling and linking, creating an executable. So inside here you'll find your binary version of your programs. Let's see what I have here now. Application, solvers, incompressible. I think I have only one, and also in my platform I have only one, I think. Yeah. So I have destroyed whatever we did yesterday. Hence, we have to repeat that one, at least the first step. So let's do that. We have it here somewhere. Copy. Yeah, we have it here. Copy the icoFoam source code. Start with that one. Copy, and then I have to go to application, solvers, incompressible, and then to this address. I will now copy the source code from icoFoam, like that. Then we should be good to go. So here is a copy of the original. You have the make folder, create fields.h, icoFoam.c. Okay, so now let's following this recipe. Let's see, we don't need that one anymore. We have it here. Well, one step we should definitely do first, so we don't forget it. That is to edit the make file. Make files. Here, we definitely need to change the setup here. So the essential one, that was this one. Add user underscore essential. And for the name of the program, why don't we give him another name? If you use the same name, then you have two versions of the same program. That may be confusing. So what should we call him? icoFoam. So then that should be my name for the new program. Save that one. Then we open the source code. Let's see now. icoFoam.c. So yeah, you have a lot of text before he actually starts doing something. First executable statement. So he has a lot of things he needs to do. Never mind that. We just take a copy now of the new solver. And it's not that many sentences. This one. Copy that one. And here I just put it at the end of the main loop inside the source here. Here you have the start of the time loop. So let's find the end of that one. Should be down here somewhere. Yeah. So whatever he's done in here, he solves for the velocity, he solves for the pressure. And before he then go to the next time step, he print out something on the screen. Fair enough. But here then I can glue in my new solver. Hopefully. No, I can't. I lost it. Once more. Copy and paste. Here we are. So this is the entire solver. You have the time derivative, but hang on, have I chosen the wrong one? Why did I choose S1? I think I did the wrong one, didn't I? That shouldn't be the one. I messed up the files. Okay, let's just change this one then. This is more for fun. They have used S1 as a variable instead of the temperature. I mean, you can call him whatever you want, but here for simplicity, I want to go back to temperature. Temperature and temperature, oops, careful. Here we are, and temperature. I have to re-edit those files. Why did I change them? That was weird. Yeah, I'll change it. It should be, of course, the temperature. But that is all we need to change in icoFoam.c. We just add a solver. Of course, we have to now define the variable. He's going to need this diffusion coefficient for the temperature. So we need some additional things here, but not in this main script. So I can just save this one. But in this guy, create fields, here we have to do some changes. Here we have to do some changes. So you can see what he's doing. Read in the viscosity, create the fields P, create the vector fields U, and so on. So now we have to create a temperature field. So in create fields, and we can do that after the velocity. Just copy everything here. Something like that. Let's see now. Here he has created velocity field U. So here I just insert the new one for the temperature. Something like that. Here we go. So now, yes, it's T, not S1 as I as I had a version of before. So it's T, And that's all there is to it for creating the field. But we need something more. We also need this diffusion coefficients. So here we add one entry into the transport properties. So let's copy that one. And where are we? Somewhere up here. Then we have to insert here the scalar dt. So here he reads the viscosity from the transport properties. Now he also reads dt from the same file. That should be everything we need, I think. Let's see now. Yeah. So let's now try to compile this one. Where are we? In the icoFoam folder, that's correct. So I just write wmake. And hopefully then we don't get any error messages. Here we go. No warnings, no messages, no nothing. Success.
This is in the folder you created
Yeah.
last lecture, right?
You see, yeah. I'm standing in, where are we? Home, applications, not the run folder. Applications, solvers, incompressible, and then where you have the source code. Yeah. If you are in doubt, I mean, you can also get a lot of warnings here, but it may still succeed. So it's maybe a little too much information. Has he created the program or not? Well, one way to check it is using which. What did I call it? Icothermal, wasn't it? Thermal foam. Just to see that he actually finds it. Yeah, and he finds it where he should, under my personal playground. Binary, yes, there it is, an icothermal foam. Of course, you can just try to run it. That's also a way to check it. Icothermal foam. Then the program starts. Of course, it crashes. You don't have any case here at all. So, yeah, but it exists. The third way to do it, if you go to your run folder and one above, you can always list under platforms what executable files do you have. So now I should have two here. Platforms, binary. Yeah, I have my icothermal foam present there. Good. Now for the simulation. Let's go into the run folder, and there I have the standard cavity. So I copy that one. Copy cavity. What should we then call it? Cavity. Call it thermal cavity. Thermal cavity. So let's go into that one. So we have the basic setup here for our straight cavity without temperature. Of course, here we need to do some changes. Let's see now. Let us kill this editor here. And then we have to do what should we do? We can start with the 0 folder. You have for the velocity and you have for the pressure. You're going to need one more. So I copy in the 0 folder the pressure into a new file, the temperature file. And let's change that one. gedit 0t. Here we are. This was the pressure. Now we have to edit this one to handle the temperature. So it must be a temperature. What's the dimension of temperature? No, nothing there, but I have 1 Kelvin here. What kind of case should we play with here? Internal field. Let's start with 300 Kelvin. Thank you. Moving wall, fixed value, and the value should be, what is it, uniform 300. No, the moving wall, we keep that one hot, 400. But the other walls, 300. Fixed value, and then value uniform 300. So then the top lid should be hot, and the other 3 walls should be cold, and yes, it's a 2-dimensional. So we try that one. Please yell out if I print something wrong here. Then it was the transport properties. We have to do something when there as well. Here I now only have the viscosity. And the viscosity here, it's, let's see now, if I recall correctly, the Reynolds number with 1 over this one, that's 100. But the size of the cavity, that was only 10 centimeters. While we're here, I changed that one to 1 more 0, so I will have a Reynolds number of 100. And then we need a new entry here. He should then be small, 3 zeros or something like that. I think that one should be correct. So far so good. What else do we need to do? Nothing more here. Thermal cavity, and then the system folder. Keep the block mesh dict, control dict. I'm going to change this one. I want to run all the way up to 2 seconds. Because there's a point, the velocity and the pressure field will be solved first. The temperature takes some time before he sort of diffuses into the correct level. So we need some additional time here. You'll see when we look at the solution. But that's the only thing I'm going to change here. But then we have to play with schemes. So here we have some new schemes. Not gradients, but divergence schemes, the transport, the nonlinear terms. Definitely he's going to need that one with temperature. So let's just copy that one and then glue him in here like that, and then we can replace U with T. That one should be okay. He will also need the double derivative, Laplacian scheme. But you see, this one is stated as default, should be covered anyway. So that's okay. Okay, then finally we have to deal with FV solution. We have to solve the temperature equation here. How should we solve that one? Well, we use the same as U. So a short version then will be, do it then like that, and put a vertical bar and the temperature. Vertical bar means U or T. So now I'm solving the same for velocity and the temperature equation. Okay, let's see if this one succeeds. Have I forgotten anything then? Let's see now. We have that one, we have that one, we have that one. No, I think it's okay. Let's try to run this one.
Can we control it?
Yep.
This says icoFoam.
Yeah, that was a good point. Thank you. Thank you. I think when I write or execute icothermal foam, I think it does that anyway. But if you have this trick with the foam run, then you have to change that one.
Okay.
But let's change it anyway. What did I call it? Thermal, didn't I? Yeah. We try. Let's see what happens. Where were we? Block mesh. The block mesh was a little small, if I recall correctly. Let's have a look at that one before we do anything. Block mesh dict. Yeah, it's 5 by 5 cells. That's a little crude. Let's go to 20 by 20. Okay, then create the mesh like that. We have 400 cells, sounds okay. And then I run icothermal foam. Let's see now. Well, he run all the way, and the Courant number looks okay. So let's have a look. What have we received here? Foam. Here we go. So here we have the pressure, and yes, we have received a temperature. We have a temperature field as well. What do you know? If you look at the velocity here, and we run, you can see after half a second, then he has received the steady state. Let's see now. Yeah. Doesn't change. Here he starts to change. So half a second, then he has reached steady state for the velocity. Now let's look at the temperature. So sort of the initial state, very close to. We have a hot top wall, 400 degrees, and then 300 for the rest. And now we play. And you see, he's even changing, even after 2 seconds. He hasn't reached a steady state yet. You still see some changes here. Not much, but a little bit. So, yeah, the temperature is sort of lagging. So, luckily then, they don't talk to each other, so the velocity and the pressure fields are independent of this solution. But it takes some time before he can organize the temperature. Okay, so that was how you create an additional equation inside a open foam or icoFoam. Any questions to that one?
You copied the pressure and altered the name, basically.
Yeah, so you can see in my 0 folder now, I have a file just called T. So just remember, change all the names, change the dimension, and then of course the different boundary conditions. Other questions? Yeah, we still have some time. I wanted to show you, what did I wanted to show you? Yeah, it was the other one. I put out this one for you. I found sort of the same problem, or the same setup, introduced temperature into icoFoam by Joel Guerrero. So he has sort of the same setup. He called it my icoFoam. Fair enough, it's just a name anyway. But he did this crazy stuff with creating a variable, new variable called S1. But why not? Instead of using T, which will be much more natural. He still uses dt then for the diffusion coefficient there. So that's at least something. And then this might also be convenient. this has to now be inserted into the this createfields.h file. And he has done something a little bit strange here as well. First creating the field, the temperature field, now called S1. Okay. But here, reading this diffusion coefficient, well, he's reading that one from the diffusion properties, and he has then, in other words, created a new input file. He doesn't use the same transport properties, just add another entry. He has created, or you have to create then, an entire new file to read this diffusion coefficient. I mean, this can be convenient if you want to have, say, an input into your program of any variable, whatever you want. Then you can create your own input file instead of messing around with the other one, like transport or turbulent or whatever. So yeah, that might be okay. And what else? Yeah, this is the standard way, changing the executable to your own area, your own name. And yes, he has a test case set up for us. I think I have given you everything here. Let's see. Programming icoFoam. Yeah, I just called it test case. So here you will then find this PDF file I just showed you. Here you will then have the entire steps you have to do, and then you have been given here the entire setup as a zip file. I just called it test case. So inside that one you find the entire setup for what I am about to show you. I think I have it here somewhere. Let's have a look. Where are we? Change directory, test, case, I think I called it. Yeah, so here we have it. So, I have to change machine. Yeah, here we are, inside my test case folder. So now I've copied everything. You have the fluent mesh. It's the elbow case, 2D elbow case. So we have the fluent mesh here. Hence, the run solver given, it won't work. I think that one is based on that the mesh from Fluent is lying somewhere yeah, way ahead in a different location. So don't use this run thing. But we definitely need to create the mesh and then just run my icoFoam. But let's have a look at some of these files first. Let's see now, where are we? Here. I can now kill that one. And then we can have a look at yeah, the 0 folder. He has the pressure, velocity, and the S1. Well, why not? Let's have a look at that one. gedit 0 S1. Because that one is quite interesting, actually. Of course, yes, it is temperature, called S1, and we have 300 internal. We have a wall 300. And then he has done something quite specially at one of the inlets. If you can recall the elbow, you had one big inlet and then making a 90-degree turn. And then we have a tiny little inlet hitting just the elbow there. So, but you see the inlet, the big inlet, he called it inlet 5, he has actually done some programming. So this is actually an option. And to going into the details here, what he actually is doing, then be my guest. I have no idea. But I can understand at least this part. So if the position here is bigger than 8, you put 300. Else, you put 350, meaning you can split the input in 2 regions. So that's quite nice. Obviously, here you can then create a function or whatever you want. So yeah, it's actually possible then to program your own boundary conditions here for the inlet. I like that one. You'll see when we try to run this one. What else did we have? We had something with the constant folder. So now we have to create another input file called diffusion properties. This was the only original one, containing only the viscosity. But now we have a new one, which then is called diffusion properties. So you see, it's actually quite possible then to create your own input file to input any parameter you must you want to play with. So here we have the diffusion. What else did we have here? Let's see now. System folder. Nothing magic here, I think. FV schemes. Let's see now. Obviously, he has tried a lot with different schemes, but here we have it. The nonlinear for the temperature using linear Gauss upwind. Here he needs the gradient, hence that one has to be also defined up here. Some of these schemes demand information how you're handling the gradients. And also the Laplacian, as you can see here, yes, we have a new entry here. And finally, the solution. FV solution should be here somewhere. Yeah, he has created his own entry here. As you can see, it's identical to the velocity, so he could have done the same that I did, just U or S1. Never mind. Let's see if we can make this one run. First of all, we have to create, what was it? The mesh. What was the notation there? The name was fluent mesh to foam, and then the name of the mesh file. Here goes. Here we have created the mesh. Some Fluent, you get some very strange names of the different patches here. But yeah, we have to address them, so we can just check the mesh. Check mesh. That was not the correct one. Check. Check mesh. Thank you. Mesh OK. And then we try to simulate my icoFoam. Oh, we didn't like that one. Well, actually, he does. He takes some time because he has to sort of execute the little snippet of codes that we had in the 0 folder, creating these special boundary conditions. But here we have simulated. So let's have a look at the setup here, the solution, parafoam, and apply. So yeah, here you have the classic case, pressure, and what do we have here? We have the velocity, and yes, we have a new one called S1. So let's have a look at the velocity first, and then play. So there you see, you have an inlet here, quite low velocity, and then a high jet coming in here, and then they sort of mix. How long time does it take before he is steady? Well, he's still running. So if we try again for the velocity, and then I stop him when I see no more changes, should be around here. So after 51 time steps, then I have a steady state for the velocity. Now look at the temperature, S1. So here you have the setup, and here you can see the special inlet. You have one part of the inlet here, given one temperature, and then another one for the rest. And let's just play with that one. Here we go for the temperature, and he should then be steady state at around here. So he used twice as long time before he reached a steady state. Very nice, I would say. And I would say the solution makes sense. Sending in cold, hot, and then you have something even hotter coming in here, and then yeah, you will get a mix, but most of it will just passively be transported here. So it doesn't diffuse much in this, say, cross-stream direction. It doesn't have time. The flow will just push it out. Okay. Any questions to that one? Then we take a break.